Hello, CIS40A. In this video, I'm only going to cover the lecture for Unit 8 as I didn't assign an assignment for this week. Make sure that you work on your subnet practice using your workbook. And in this chapter, I'm also going to use the author's technique. And whichever technique is easier for you, you can use it for the subnet. So to start, we're going to define subnetting, which is a way that we would use an IP address range, and we can use it to expand the number of addresses that we can work with by dividing that address range into multiple ranges. And we can implement it for the physical locations, or we can use it to really divert some of the network traffic so it is not in one large network, but it is in multiple smaller networks. So that way we can reduce the traffic that would be congested. So the subnets, when we're using the host bits on the subnet mask, this is when we are using what's called a masking technique. And in subnetting, what we're doing is we're borrowing or we're leaning into the host bits from the network bits. So we might go over a couple more bits so that way we can expand our networks. And that would consider to be a classless type of address in that it doesn't belong to a specific class. So what I had noted on the first page is the step to subnet. And to start, what we want to do is we want to determine the number of host bits that would be required for the amount of subnets that we need. Let's say that you need 4 subnets, then we can use 2 of the mask bits. That means that we're going to borrow into the host identifier by 2 bits, as I highlight that in teal here. And we are going to convert the subnet mask to binary. So we would take 255, 255.00, which is the subnet mask for Class A address, where this IP address, we want to use this to divide it up into 4 subnetworks. So first, we're going to need to determine which is the network identifier. That's the 255. That's the first octet. And the rest will be the host following Class A. So now if we move away from that class, if we lean into the Class B or going into the host bits, we are going to have to borrow 2 bits in order to expand our network to 4 subnets. So that means that we will separate our larger network into 4 subnetworks, and we would use the routers or level 4 switches to be able to interconnect our 4 networks. So what we will do next, after we determine the number of the borrow bits or the mask bits, we would then convert the subnet convert the subnet with the borrow bits in binary. And so if you take just this octet and convert that into binary, from binary to decimal, you would see that it's going to be 192. So we already had that in binary here. So when you determine the borrow bits, you are going to take that octet and convert it to decimal. So what you will have is you will have 255.192.0.0. And a quick way to do this is you would open up your programmer calculator and you would hit bin for binary, and you can put in 11000000, and that will be our 8 bits. And you would see that it's going to be 192. So the second octet will be 192. And then the rest, which is going to be 0. So our new subnet mask is going to be 255.192.0.0. And that has been changed from the Class A subnet mask as we borrow 2 additional bits. So once we have the new subnet mask, we need to take a look at the variations of how we would have these 2 borrow bits. They both can be off. They can be off and on, so it might be 00 or 01 or 10 or 11. And this is going to represent the decimal of your IP address in that in that IP range. So what we will do next is we are going to convert all our host bits to 0. So as we talked about this in the lab, we mentioned that the 0 at the end are going to be your network IP. So to determine the network IP, we have to take a look at all the variations. So that's going to give us each of these are going to represent one of the subnet. Okay. So if you take a look at my table on page 2, you would see that we are going to keep the first octet the same, so that will be 10. And we need to take a look at the binary values of the subsequent octet, the second octet and the third octet and the fourth octet. So if we look at the first variation, that will be 0, 0. Then here we simply put everything to 0. We switch everything to 0. So you would have 10.0.0.0. That will be the first subnet network address. For the second subnet, what we need to do is we need to take a look at the 01, which is the second variation. That will be our second network. And if we convert this from binary to decimal, we would have a 64. So then we would have 10.64.0.0. And where did I get this 01? Because it would be one of the variation where we would be able to borrow the 2 bits into the host. Then we need to take a look at the third network or the third subnet, and that will be the variation of the 10. So the 10 will be here after the first octet. And if we convert this octet into decimal, we would have 128. So our network address, when you put all the last bits to 0, that's what it tells you here, then you would have 10.128.0.0. And lastly, our subnet 4, which is going to be the last variation, 11. And this is going to convert to 192, because if you punch this value into a calculator and convert it from binary to decimal, you will find that it is a 192. And that is our last variation. So as you can see, once you determine the borrow bits, you come up with the new subnet mask. And then from that, you are going to look at the variations of the borrow bits, and that's going to give you the octet value for your either network address or your broadcast address or your range. So then the next type of address that we're going to look at is going to be the starting usable address. And here the note says that the least significant bit, the most right-hand side bit, needs to be set to 1, and all the other bits are going to be 0. So I got to make sure that on the fourth octet, my most right bit are going to be set to 1. And we are going to keep just like what we've done previously, we're going to keep the variations included in the second octet as we borrow into the host there. And then also the third octet would stay the same. So we simply just add the 1 to the least significant bit for the starting address, which gives us the first subnet starts at 10.0.0.0.1. The second subnet starts at 10.64.0.1. As you see, that would be its network address there. And then the third subnet would start at 10.128.0.1, and the last subnet would be 10.192.0.1. So we simply can change the least significant bit, the most right-hand side bit, to 1, whereas the network address, we would make sure that the right-hand side bit is going to be 0. Then after that, I need to determine the last address in each range for each subnet. So here it tells us that the least significant of the host bit needs to be set to 0, and everything else is going to be changed to 1. So in the first subnet, I know that this came from the variation that I looked at earlier. So 0, 0, and then everything else, I wanted to make sure that it's going to be 1, except for my least significant bit, which is 0. So the most right-hand side bit, that needs to be 0, and then everything in between from the borrow bits to the next to the least significant bit, bit number 2, that's going to be all 1s. So that's going to give me 10.63.255.254. We have to set this to 0 because if it becomes 1, then it will be 255, and that will not be a usable address. So my first range is going to end at 10.63.255.254. And you notice that that will be the next value, that will be the start of my next subnet, which is the network. Okay. So the way that we look at the range is it's going to go from the network address to the first usable address to the last usable address, and then the broadcast address. That will be one group. And then we would have the second subnet and so on. So again, for the subnet 2, what we're going to do is we're going to keep the borrow bits the same. We're going to change everything to 1s, and then we're going to make sure that the last bit on the right is going to be 0, which gives you 10.127.255.254. And if you take each of the octet and put it into your programming calculator as binary, you should be able to find the decimal value that would represent your IP address. And then subnet 3 would be the same. We keep the borrow bits as we noted in the variation. We put everything to 1s, and we're going to keep the right-hand side bit to be 0. So we would have 10.192.255.254. And subnet 4, same process. The first octet is 10. We don't touch that. The last variation of our borrow bits is 1, 1. And we're going to convert all the bits to 1, except for the most right-hand side bit that will be 0. That's going to give you 10.255.255.254. So once we have the last usable address in each range, then we are going to find the broadcast address, which should be right after this one. So we can quickly note that it would be right after the last usable address, as you can see. So in the first subnet, my broadcast address is going to be 10.63.255. 255, it's 1 after this. So the difference between the last usable address and the broadcast address is that the most right-hand side bit is going to be also on. So we're going to put everything to the right to be 1. And so you would have subnet 1 is this. Subnet 2 is 10.127.255.255. Subnet 3 is 10.191.255.255. And then subnet 4 is 10.255.255.255. So once we have the network address, the usable addresses from start to end, and the broadcast address, we can work on our CIDR. And so when you look at the CIDR, going back to our borrow bits, so our borrow bits really is, we have 255.192.0.0. And here in the host, we borrow 2 bits along with the 8 bits from the network. So that's going to give us the 10 bits. So our CIDR will be /10. Now our host bits would be 22 because it is 32 bits in the IP address, subtract the 10 bits for the network, which gives us 22 bits for the host, what's left. Now the number of hosts, once we determine the host bits, we simply use 2 to the power of 22, and we are going to subtract 2 because for every range we cannot use the broadcast or the network, so that's going to give us this many addresses in each of the range. Okay, so the usable address, that would be 4,194,302 for each of these subnet. So when we put it all together, you would see it would look like this. So my subnet 1 is going to, the broadcast is going to be all 0. My range is going to start at 1. My N is going to be 10.63.255.254. My broadcast is going to be 1 bit higher than the other. So it's going to be 10.63.255.255. We found the usable address, which will be 2 to the host bits, subtract 2, which gives us this many IP addresses that we can use for each of the network, and our subnet mask. And so as you can see, once you put it together, you would see that it's going to go from the network address to the range start, to the range end, to the broadcast address, to the number of addresses, and we would then have the subnet mask. So this is a technique where you would implement more of the decimal and binary conversion. And so it would be easier if you visibly see it, either using a table or write it out. So you can practice using this technique as well. Now, we had mentioned that we had been working on converting your regular classful address to something that has host mask, which is a classless address. So the difference between the two is that a classful address uses IP in class A, class B, class C with the default subnet. A classless address uses, it's a 2-part view for the IP addresses. It would use the first octet, and then subsequently we would be able to borrow the bits and represent an IP that doesn't belong to any of the class. It doesn't necessarily belong to A or B. It is a classless address. So here, let's differentiate between classful and classless. And in classless routing protocols, we would see that the routers would use classless routing protocol to advertise the mask information to each of the subnet. And it's going to use what's called the VLSM, and the route summarization to be able to identify the network that has the appropriate subnet. So it would also use to increase the usability of the subnets. And VLSM is mostly used in a network where we would have multiple subnet masks. Okay. So here makes some additional notes about classful and classless routing. So classless and classful routing, we're going to see this in the configuration, and when we did the lab, we saw some of this. This is a process of how IP routing uses the default route, and that can be changed based on the router configuration. So classful routing, the packet's destination only matches the default route, and it does not match any other route. So it's going to follow the default route, just like how we talked about IP address. It uses default subnet mask. So the classful routing uses the default route, and if the router does not know any routes in the classful network in which the destination IP resides, then it will not be able to match any routes. So it has to know the default route. With the classful routing, we would use the classful IP addresses like A, B, C. And the destination matches the default route. So it would then use by the router, and it doesn't require any additional subnet information. In the classless routing, the packet's destination only matches the router's default route, and it does not match any other routes. It forwards the packet to the default route. So when you compare these two, and it's easier to see it in a table, for the routing, the IP forward is restricted on how it's used the default route for the classful. In the classless, the IP forwarding process has no restriction in using the default route. In the classless type of protocol, you would see that would have RIP2, IEGRP, and OSPF. Whereas the classful, it uses RIP version 1 and IGRP. Whereas the classless uses enhanced IGRP, and later on in the notes it will talk about the routing protocols. So earlier we worked on the CIDR. CIDR stands for Classless Interdomain Routing. Make sure that we know this for Network Plus. And this is going to be based on your VLSM, which would be a specification of the arbitrary length of the prefixes in your subnet mask. So this is a newer method to really denote the subnet mask. So when we say 192.0.2.0 with the /24, we would know that 24 bits of the subnet mask would be on. So it will be 255, 255, 255.0. And we can also use CIDR for version 6, in that it also uses the slash to indicate the bits that will be on as part of that network. And that will be your network identifier bits. So as you can see, this is really a way for us to reduce the number of entries in the global routing table, as if you put in many of the subnet masks, it would require a lot of the storage for the subnet mask. So routing is really a process for the system to select a path that will be able to forward the traffic between the networks. And router does this, it will communicate with other routers in its surrounding area, or so that way it can forward that packet to the right destination. There are two types of routing. You have the static route and you have the dynamic route. In small networks, we can configure the routing table by adding the static route. And in a larger network, especially if your topology is more complex, changing the routing table is unfeasible. So we would then use dynamic route for the larger network. And dynamic route allows the system to utilize the protocols and to be able to implement the algorithm for routing to be able to forward the right destination, whether it's looking for the shortest path or it's looking for the distance vector. So in dynamic routing, you would see the algorithms such as your RIP, your Routing Information Protocol, version 1, version 2, Open Shortest Path First, Enhanced Interior Gateway Routing Protocol, your EIGRP. So what are the differences in the algorithm? You will have protocols that uses distance vector algorithm, and this approach assigns the number of each of the links between the node and the network. So think of it like each road has a number of miles. And we are going to be able to calculate the total number of miles or the total cost to be able to travel down the path where we cross many roads. So the system, what it does is it would assign the cost value for each of the link that it's connecting to. So if we have 30 hops, then each of the hop would have a certain cost value, and it would take a total of that cost value and be able to determine the distance vector that will be appropriate to send to the destination. So each of the router would then notify its neighbor node of the assessment of the cost. So it's going to say, this is my cost value, 5, for example. And so the routers, they always going to advertise that to other router, and the neighbor router is then going to examine the information, compare it to what it knows on the routing table, and then to be able to see if that cost is going to be feasible for that particular path or route. And in the distance vector, any node can be used. So in the case where some node goes down, it can update the information by looking at all the adjacents, note all the neighbor. For the linked state algorithm, this is a different algorithm. It applied graphical map of the network using fundamental data from each of the node. So it's able to map out by flooding the entire network with the information about other nodes that it can connect to. And the node would then independently assemble the information into the map. So that way it would be able to use that map and determine the least cost path. So unlike the distance vector, it elevates it by using a linked state map. And that path is then going to look at how it would send the data from start to end. So the third type of algorithm is called the optimized linked state routing algorithm. This is the OLSR. This is used for a mobile ad hoc network, and it's used what's called the hello and the topology control messages to discover and disseminate linked state information. So it is a linked state routing algorithm, But what it's going to do is going to communicate based on the two neighbor. So it's going to say hello to the two neighbor, and it's going to relay the information about the communication across the two neighbors. The next type of algorithm is called the path vector protocol. This is a combination of distance vector and linked state, and they are intra-domain protocol. This is used inside an autonomous system, which is different than your router. And routing protocols are utilized in a larger network, and it cannot be used in the intra-domain routing. So your normal protocol that would hit the network, the larger within the network, it doesn't really work appropriately when we're crossing over the interdomain. We're crossing over many different type of network like ISP. So link state does the flooding. Distance vector would then look at the hops and be able to look at the costs. Path vector routing is used in the intradomain, and it assumes that one of the node in each of the autonomous system is then, it acts on the behalf of each of those nodes. And those are called the speaker node. And it's going to use the speaker node to communicate with other speaker nodes. And it's going to advertise its path, not the matrix. So that way the other routers will learn about its path and be able to communicate. So here it expanded more on the path vector algorithm. So for CCNA, CCENT, and also networking, make sure that we know the difference in the algorithm for the routing. So some of the terminology that you need to be familiarized with is first, loopback interface. This is the network interface card that is connecting to different networks to send data from one network to another. And it can be used for testing purposes. Routing loops usually is a problem in the network, and they are created by errors in the routing operation of the routing algorithm. Routing tables is a table that stores routing information, network host, the routes, the destination, and so on. Now, it can contain static route, and it can contain network topology, discover, and just in general information about the routes. The default route is a configuration in IP that establishes a forwarding packet when no specific address of the next hop host is available. So it doesn't really necessarily know that it's going to get there, but it's just going to go the usual path or the default path to get there. The protocol data units is a single unit that transmit among peer. PDU consists of protocol-specific control for the information and the data. And each implementation of the protocol is tailored to specific mode of the data exchange. Maximum transmission unit, your MTU, is a measurement that represents the largest data packet that network connected device will accept. Okay, maximum transmission unit. Your protocol data unit is going to be customizable to the data. Now, Windows have its own internal router. You can find this by using command prompt, and you can simply put in the command that's suggested on your notes, which is going to be route print to display. You can manually add the route, but you have to specify what that route is, or you can delete the existing route. So if we simply do route print, we would get the information about our routing table that would be stored by our system. Now you can also use the server to set it up as a router. In that case, you will need two network interface adapters, right, for in and out, and be able to set that up as a routing server. Convergence is a state to set the routers that have the same topological information about the internetwork in which they operate. So if a number of the routers converge, they have to have all the available topology information from each other between router A and router B to be implementing the routing protocol. It must not contradict one another's topology, and it would establish an agreement. So that way, those two routers or those multiple routers will be able to communicate as it's already aware of the topology. Dynamic routing protocols consist of two categories: your interior gateway protocols and your exterior gateway protocols. Interior gateway protocols are used in dynamic routing between the routers to run on TCP/IP hosts within the single autonomous system. So what does this mean? This is a type of protocol that is used with the dynamic route, and the routers would then use the protocol to exchange the information about the routes itself. So the protocols could be RIP version 1 and 2, and RIP is a distance vector algorithm. It calculates the best path to send based on the number of hops in the path. Now, RIP version 2 is better than RIP version 1 in that it is an improvement. It's more stable. In Cisco router, you would use router RIP to be able to use that feature on the router to route using RIP protocol. There is also IP version 6 RIP. Open shortest path first, your OSPF, uses link state and the shortest path first algorithm. This is faster than using RIP in that it converges after the network changes. It is a little bit more complex to configure, but you commonly see open shortest path first being used. It's just going to look at the quickest way to get there and making sure that it sees that path as the shortest. So it's going to compare the path and the cost of each path, and it's going to determine the open shortest path. We also have IP version 6, open shortest path first. Now, another protocol that you can look at is the interior gateway routing protocol. This is a distance vector gateway protocol. This is proprietary to Cisco. And they designed this to overcome the limitations of RIP version 1. Now, IGRP uses all addresses within class A, B, and C network. Now, the subnet mask would then be configured at the interfaces level compared to classless routing protocol that can use variable length subnet mask or VLSM. So classical protocols would then be required to be used in IGRP. So you cannot have non-default subnet mask. Enhanced Interior Gateway Routing Protocol, your EIGRP, is the improvement of the IGRP. It is Cisco proprietary protocol, and unlike RIP, it sends updates periodically, which reduce the workload for the router to be able to obtain the data about its neighbor. Another set of protocols you can look at is your exterior gateway protocol, and this is the second category, as we mentioned earlier. This is used for autonomous system, and it's used to share information about other exterior gateways, so that way it can forward the information. Routing use matrix, which is a way that it keeps track of cost values by routers that determine the best path. And matrix is just a way that it stores and assess the information, so that way it would look at hops, bandwidth, delay, reliability, load, and cost of each of the route. So simple matrix is used in RIP version 1 and 2, while complex metric is used in EIGRP. Now here it talks about RIP version 1 and 2. It's not suitable for networks that have a lot of transmission and have on the redundancy path. So by default, EIGRP uses a minimum bandwidth, and it accumulated the delay in the data in the path for the destination network using the matrix, which stores the cost information for that path. So because it is using minimum bandwidth, it's going to be the slowest compared to some other protocol. So this is how you will be able to calculate for the weight value for EIGRP. You can also click on the link. There are calculator for those type of system as well. So now we're going to look at, so in the matrix, you would also have bandwidth and delay. And bandwidth is used based on the formula, in that when we're looking at the bandwidth and we're looking at delay, we want to use the formula to sum up the delays in the path, and that will be stored into the matrix for evaluation. The hops is just a value that would be measuring distance based on the number of networks that the datagram would traverse. So each of the router can represent a single hop, but also a segment can also represent a single hop. Now, the administrator would then affect how the router can make the decision by putting in an arbitrary value or values of cost to the matrix. Here it also talks about load, and load is measured over 5-second window. It is a value that's able to determine the traffic from load. So when you have the value 255 is 100% load utilization, compared to 1. So the higher the value, the higher the traffic load, compared to 1 where it's going to be minimal load. Bandwidth is measured in terms of per second for how the transfer would be. So if the protocol is considered to be utilizing bandwidth capacity, then it's going to take a look at each link, each path, end to end to determine whether the higher the bandwidth, the faster it's going to get selected. So the lower the bandwidth, it will not be chosen for the best route. So the router is going to look for the path that's going to have the higher bandwidth. And there's also a value for reliability where it's measured over time frame, over 5 seconds, on how reliable that transmission would be. So in the case where you have failures or errors or lost datagram, the routers would then observe that and report the problem. Administrative distance. In administrative distance, it's a way that we would use the value in the case of EIGRP, which is a Cisco proprietary technology. So the route for EIGRP, it uses a value which is administrative assistance of 90, whereas RIP route at a higher administrative assistance. So each of the algorithm would require a certain value for administrative assistance. And the router would need to find and select the better path in multiple paths. And distance, administrative distance is a way that it's able to determine that. Shortest path bridging, your SPB, is a specified standard. It is in the replacement of spanning tree. And it does have a faster convergence by looking at a larger two of the topologies to support the convergence time. So it helps in traffic load and also sharing all paths on the network. So this concludes my lecture. This chapter was generally looking at some of the technique in subnetting and also your routing protocols and algorithm. Make sure that you can distinguish the differences because Network Plus and other certification like Cisco CCNA would require that. And it helps to really, define each of the protocol and remember or memorize each of the protocol, what it does. And when you configure the router, if you remember what they are, hopefully it makes more sense for you to be able to use it. Now in the textbook, it also shows some exercises very similar to what we've done in the lab. You can utilize those exercises with your packet tracer to be able to examine your router, your switches, and so on. There are also subnetting exercises from the book. So whichever technique that you would prefer, if you want to use the workbook for exercise that we've used in the first lab, or you can use the textbook information and be able to do that, which I included in this set of notes when we were doing the conversion with all those tables at the top. Thank you for watching this video. This concludes my CIS40A Unit 8 lecture. And again, we do not have to complete the assignments this week, but I will make sure that the information is going to be available for you in the future review for the final exam.